All right, guys. Today we are going to take a look at what happens when you're taking a limit of a function, and instead of approaching what we called an a value, instead of x approaching a number like 2 or -7 or 11, what happens when x approaches infinity? Now, we saw this a little bit when we had pictures of the graph. When we had pictures of the graph, we could just look at it and see, was the graph flattening out? Was it going up? Was it going down? But if I don't have a picture of the graph and I just have the actual function, what's going on? Now, most of you guys from your study of polynomials have an idea of what polynomials are doing. Okay, for example, all right, most of us know if we're dealing with a polynomial like, 3x to the fourth plus blah, 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 because it's an x to the fourth and because it's positive, if you remember back on your study of polynomials, positive coefficients mean I'm going up to the right. And the fact that it's even, no matter what it does somewhere in the middle, it's eventually going to go back up in the same direction as the right side. So if I were to ever ask you what is the limit of this function that was 3x to the fourth plus whatever, as x went to infinity, you could say, well, I know about polynomials because it's positive, it's going up to the right. You could say, well, as you go to infinity, you're going up to the right, and up to the right would mean that you're approaching infinity. And if I said, what happens when you go to negative infinity? Well, because you know that even powers also go in the same direction as the right behavior has the same left behavior, you could also say it's going to infinity. And you could do the same process with something like, maybe something like 4x to the third minus 2x squared, yada, 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 or whatever. I'll make it negative. How about this? So on this one, because it's negative, you know that it's going down to the right. You know that, okay? But because it is an odd power, you know that it may do some weird stuff here in the middle, but heading left, it's going to go in an opposite direction. So if I were to say, hey, what's the limit of this function, this negative 4x cubed, blah, 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 as x approaches infinity, you know that because it's negative, I must be going down, so it must be going to negative infinity. However, if I were to ask you the limit of the same function, okay, as x goes to the left, you know that because it's going to the left and the odd sends that in an opposite direction, you must say, oh, well, instead of going to negative infinity, it must be going up to the left, which would mean positive infinity. And that's how you deal with polynomials. Now, polynomials are pretty straightforward. What's not as straightforward are rational functions. So that's what we're going to focus on a lot in. Now, you do know some things about rational functions. And again, rational functions look like polynomials over polynomials. So and by the way, I'm on page 15 in the book. All right, and you'll see it, Limits Part 3 at the top. And you could read through this and figure this out, but the bottom line is all graphs, as they head to the right and head to the left, if they're polynomials or rational functions, they're either have really three choices. They can go up to infinity, go down to negative infinity, or they can flatten out. And if you remember what you learned about rational functions, they behave according to their asymptotes. And a lot of times they have horizontal asymptotes. Now, horizontal asymptotes means the graph is going to flatten out. And if it flattens out, then the limit as x approaches infinity would be whatever the y value of that horizontal asymptote is. So essentially, you can just find the horizontal asymptote if there is one. Now, if you remember your rules for finding horizontal asymptotes can be found in two situations. One, when the highest powers in the numerator and the denominator are equal. And when they're equal, if you think back, they always had horizontal asymptotes equal to the coefficients of those powers. So if the horizontal asymptote of a function like this was 2/5, then we can say the limit as you approach infinity or even negative infinity is 2/5 because it's going to follow that horizontal asymptote either way. Great thing to remember. All right, now, what happens when the number on the bottom, the n, is bigger than the exponent in the denominator is bigger than the exponent in the numerator? Well, basically, that just means that the denominators is growing at a faster rate. All right, but you just learned this as the horizontal asymptote would always be y equals 0. All right, and I think we even talked about it in class, like what would happen if x was 1,000. Basically, like I was giving somebody, like in this case, if I was giving somebody $1,000, you can see $1,000 raised to the fourth power is so much bigger than $1,000 raised to the second power. So because this is such a bigger number, right, than something like that, as x approaches infinity or even negative infinity, if the bottom is growing at a way faster rate than the top, doesn't matter how big the top is. If it's growing way faster, or it's so much bigger on the bottom, then the fraction itself is going to start approaching a value of 0. And that's why it would have a horizontal asymptote at y equals 0. All right, and again, horizontal asymptotes go both ways on rational functions and polynomials if they exist. So it doesn't matter whether I go to infinity or negative infinity, I could say that this limit is 0. All right, so one more time. Powers are the same, then the limit, whether you're going to infinity or negative infinity, is always going to be the coefficients, a over b. So 2/5, you can see that right here. And then if the power is bigger on the bottom, like in case number 2, we can always say that the limit is going to be 0. And that's true again, whether I'm going to infinity or negative infinity. Now, what happens when the power is bigger on the top? When the power is bigger on the top, what that means is there's not a horizontal asymptote. So you can't use these rules. You have to start thinking about what does it mean as far as the graph is concerned. Well, if the power is bigger on the top, remember, there's only 3 things the graph can do: flatten out, go up, or go down. And what we've just talked about in examples 1 and 2 are when it flattens out. Well, what that means is example 3 is it's growing faster on the top because it has a higher power. That means that this right here, example 3, is going towards either an upward direction, which means it's going towards infinity, or it's going in a downward direction, which means it's going to negative infinity. All right, and we don't know yet, but we know it's one of those. So what we're going to do is just kind of figure out which direction it's going. And if I can figure that out, I can just take that direction, positive or negative, and put it on the infinity sign, and I'll know what the limit is. All right, so for example, on this one, a really quick way of doing it, and then I'll show you kind of a calculus way of doing it that I learned in calculus, and a lot of textbooks teach this way. But think about it. If I were to plug an infinity in for x in all of these, this x here is going to be so much smaller than that x cubed. And obviously, -5 is so much smaller than that x because x is going to infinity. X is getting huge. Same with that -1. All of those values pale in comparison to these two. So one thing to think about is, since I can't really plug an infinity in, because I know it's growing faster in the numerator, I know it's either approaching negative or positive infinity, I got to figure out whether it's plus or minus. So what I do is I kind of think about everything other than the higher powers as just a bunch of blah, 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 blah. And I think, what would happen if I plugged an infinity in there and an infinity in there? Well, on the top, I'm going to get a huge but positive number. All right, way bigger number than the denominator because it's a higher power, but it's positive. Now on the bottom, I'm getting a huge number, but it's a negative because it's -6 times that. Well, if I have a plus over a minus, that gives me a minus. And because it's huge on the top, not quite as huge on the bottom, it's definitely approaching a negative infinity. But it's those lead signs, the 3 and the -6, that tell me that it would be a negative infinity. All right, now, I'm going to go back to this same problem. Had I plugged a negative infinity, had x been going to negative infinity, look at this. On the top, what happens if you plug a negative infinity in there? Well, I get a negative huge number cubed times 3. That's a negative. On the bottom, I would get a negative squared, which is positive, but then times -6, which is negative. And I would have a negative over a negative, and it would end up being a positive infinity. So you can actually get a limit that's different from either direction, depending on which way I'm going. That was not true in example 1 or 2 with horizontal asymptotes. Because if on polynomial and rational functions, horizontal asymptotes are what are going to determine the direction either way. But when there's not a horizontal, you actually have to go and check each way. But the good thing is, it's going to be either infinity or negative infinity on horizontal or rational functions. Now, if you wonder, on a rational or polynomial functions. If you wonder why I keep saying rational or polynomial, well, it's because there's all kinds of weird graphs that don't behave like these. And we'll get into those later. All right, but right now we're focusing on what happens when we're dealing with polynomial and rational functions, these being rational. Okay, now I'm going to go over a couple of examples in a second, but what I also want to show you is a way you could do these problems. And you'll see, I learned this in calculus. The AP 5 Steps to a 5 review book shows this process this way. And it's not as quick, but it is a way to get your answer on these without as much thinking. It just takes more time. So I think knowing these rules are really valuable, and you already know them from pre-cal, but I will show you the calculus method as well. All right, so if you turn, flip this over to, I believe it's page 16. Page 16, if you go to the top, all right, there's a couple things I want to talk about before I get into this. This is page 16 in the book, all right? And that is, doing it this way, you got to have a couple of little rules down in your head to get there. But then after you have these little rules down, you can use the same process, and you don't even have to notice whether there's a horizontal or not. You can just do the process, and it'll work itself out every time. So I think these little rules I'm going to run through quickly for you are going to make sense, but let's take a look. So the first one, sorry, it has a hole punched out of it. It says the limit of x as x approaches infinity is what? Well, obviously, as x gets bigger here, x is going to get bigger there. So if x goes to infinity, I'm going to infinity. Same is true for negative infinity. So that should make sense. These two we've kind of touched on a little bit already. What happens as x becomes an increasingly bigger number? Well, the actual value of the fraction gets increasingly smaller. So you'll see that like as 1/10, and then I get to 1/100th, 1/1000th, 1 over 10,000, 1 over 100,000, 1 over a million, 1 over a billion, 1 over a trillion. The value of that decimal is getting closer and closer to zero. So remember, a limit is not what it's equal to, it's what it's approaching. So it's approaching zero. Now here, that's also true, zero, because as x goes to infinity, obviously raising infinity to a higher power would make it even bigger, right? So the bottom line is, if the top part is growing faster than the bottom part, what this really means is if I just have a number on the bottom, okay, a number being positive, like positive 2, if the top is growing faster than a constant, then I'm going towards positive infinity. If the top is growing faster than a negative constant, then I must be approaching negative infinity. Now, if the bottom is growing faster than a constant in the numerator, well, if that's the case, it doesn't matter whether it's plus or minus anywhere. If the top is growing faster, just like over here, that is becoming a increasingly smaller decimal, and it's approaching zero. And that's also true whether I raise it to a power or not. So you're going to see a whole lot of this in a second as we're doing these problems. So let's look through these examples. I've given you an example of each kind of problem. Notice here, power bigger on the top, power bigger on the bottom, power the same. And I'm not even going to acknowledge what has a horizontal asymptote, what doesn't, okay? And this is a way I was taught in calculus. They said, all right, because we have a fraction here, by rule, I'm allowed to do something to the top as long as I do the same thing to the bottom. It's kind of like multiplying the top and the bottom by 5 or multiplying the top and the bottom by 1/5. As long as it's the same on the top and the bottom, the fraction would remain the same. Okay, now again, this is a strategy when I'm going to infinity. We don't do any of this if I'm approaching 5, right? If I'm approaching 5, just plug the 5 in, see what happens. All right, so what I'm going to do, and I'm going to do this on all three of these, is I'm going to ignore the numerator and look at the denominator. Highest power in the denominator, I'm going to divide every term by that value. So notice here, highest power in the denominator was x squared. I'm dividing that, and that by an x squared. And you can see me do this. And then what I'm going to do is go through there and cancel every x that cancels. So I'm going to cancel both of those out. Nothing cancels there. Nothing cancels there. I can cancel one of the x's out here, and I can cancel two of the x's out there. And then I'm going to bring over what I have left. So I'm bringing over a 3x, a 1 over x, a negative 5 over x squared. Everything canceled there but the negative 6, and I'm bringing over a negative 1 over x squared. Now I'm going to think about what would happen as I plugged an infinity in. Well, like we learned in our rules across the top, 3 times an infinity, huge positive number. 1 divided by infinity approaches 0. 5 divided by an infinity squared approaches 0. Negative 6, there's nothing to plug in, so I'm going to bring that over. And then 1 over an infinity squared. 1 divided by a huge number approaches 0. Well, all I have left is a huge number over a negative number. So a huge number over a negative number, like we saw in our rule above, is going to approach negative infinity. All right, let's try it in example 2. Example 2, highest power in the denominator is x to the 4th. I'm going to divide every single term by an x to the 4th. Cancel everything that cancels. So that would cancel, leaving me an x squared. No x's cancel. All the x's cancel. One of the x's cancel, leaving me an x cubed. Nothing cancels. I'm going to bring everything that's left. 5 over x squared, 4 over x to the 4th, 6, 2 over x cubed, 1 over x to the 4th, and the appropriate signs. Now, what happens when I put infinities in here? Well, all of these, the bottom is growing faster than the top, right? All those 4 go to 0. 6 does not. So I end up with 0 plus 0 over 6 plus 0 minus 0. Well, that gives me this. And what's 0 divided by anything? 0. Same thing on example 3. Okay, if highest power on the bottom, x to the 4th, I'm dividing all 6 terms by x to the 4th. Cancel all of that. Cancel 2 of those. Nothing cancels. Cancel all of those x's. Cancel 1 of those. And none of those. Bring over everything that remains. Okay? At this point, what happens when I plug a negative infinity in there? Well, whether it's negative or positive, isn't the bottom growing faster than the top? And what did we say? Whether negative or positive, if the bottom's growing faster than a constant number, like a single number, doesn't matter about the signs, what do they go to? They go to 0. So all of those fractions, this one, this one, this one, and this one, all go to 0. What am I left with? 2/5. Now, if you ask me, doing it the other way, what happens as I go to infinity or negative infinity when the powers are the same? Choose the coefficients. Done. What happens when the power is bigger on the bottom when I go to infinity? 0. Done. And what happens when the top is bigger? Well, ignore everything else. All right, and think what would happen. I know if the top's bigger, it's either infinity or negative infinity. I know that. All I need is the sign. Well, if I plug a huge positive number there, I get a huge positive number. If I plug a huge positive number there, square it, and then multiply by a -6, I get a negative. Plus over minus is minus. Since I already know that it's either positive or negative infinity, must be negative infinity. So I think the first set of rules is a lot quicker, but many books and college professors will teach you this way. And there are also some uglier problems that we run into in AP Cal where this kind of thinking is pretty helpful. But I wanted to show you both ways. Some of you love this, but just know, or some of you may like this, but just know the process here is a little bit more tedious unless you're kind of doing a lot of it in your head and just writing out the results. All right, so flip the page, and I got a couple examples I just want to run through. I'm probably not going to do it this way for now, but just remember this page 16 because I am going to refer back to it at a later date. All right, so I want to throw you just some practice problems. This is page 17. Anything I don't do will be your homework. The keys to this are on Schoology. You can go find them, but I will do a few of these. And if you'll notice, these problems kind of look like piecewise functions because they have different pieces, but they are not. These are all rational functions, and the equations to these are below the actual graphs. So I'm putting them on there just to kind of give you a nice visual of what is happening, but I don't really think we need the graph. All right, so let me just look at this. What happens? I'm going to infinity or negative infinity, same problem. What happens when the powers are the same? Well, we don't really need any of the rest of this. We can look at that and say 5/2. But look at the graph. It was approaching a horizontal asymptote at 5/2, whether I'm going to the right or to the left. So both of these limits are equal to 5/2. Okay? Now I kind of want to jump over to this one. Look at this right here. Ignore the graph for a second. What happens when I go to infinity or negative infinity and the power is bigger on the bottom? Oh, well, that's a horizontal asymptote at y = 0. So whether I'm going to the right to infinity or to the left, negative infinity, both of these are equal to 0. And you can see that in the picture. Horizontal asymptote, y = 0. All right. Now, if you look at 2 and 4, both of those have higher power. Actually, this one has a higher power in the numerator. This one has the same power. But so let's jump to 2. This one has a higher power in the numerator. So I know right here that this particular graph is going to have it's not going to have a horizontal asymptote. This particular one ends up having a slant asymptote. But even if I didn't have the picture to that, I could say, well, what do I do when I go to infinity or negative infinity and the higher power's in the top? I can ignore all of this, and I know that the graph is either going up or down because it doesn't have a horizontal. So I know that the graph has going to be an answer of infinity, either positive or negative. Same thing with this one. Well, let's figure it out. If I were to plug a huge positive number there and there, I get a positive squared times 3, that's plus. I get a positive times 6, that's positive. Two positives must be going to positive infinity. But here, look what happens. If I plug a negative in there, what's a negative squared? Positive times 3, positive. What's a negative in there times a positive 6? Oh, negative. What's a plus over minus give me? Negative infinity. And you can see that in the graph, how going to the right, it went to positive infinity. Going to the left, the limit is negative infinity. All right? And then jumping over here to number 4, again, powers are the same. I can just use 3 over 1, 3 over 1. Both of these have a limit of 3. And sure enough, you can see the horizontal asymptote was 3. All right? So anyway, hopefully you understand those rules. I'm basically going over those again in 5, 6, and 7. And I'm going to leave you to do some of these problems below on 8, 9, 10, and 11. And I'm going to jump to piecewise limits and talk about them for a second. Now, as you might remember with piecewise functions are basically all kinds of different functions that come together, or maybe they don't come together, but that are different parts of the graph defined over different parts of the domain. So unlike rational functions that have certain behaviors where they separate, like vertical asymptotes or holes, these could be doing anything. Okay, they might have a vertical asymptote. They might have a hole. They might connect. They might have what we call a jump. And a jump in the graph is where, like, one graph, like maybe it's a parabola, might be cruising along like this, right? And then stop. And then another graph might just be a point on the graph. It might look like this. And then the other graph might pick up here and might be a line and look like this. All kinds of weird things could be happening. And a jump is where basically it hops from one spot to another spot and then continues. Okay? So all kinds, so this part would be considered a jump. But who knows what they're going to do? And since I honestly don't want to graph, complete the square and graph the parabola, I don't want to do any of that. So what I'm going to do is say, all right, what do I know about these graphs? So right here, I asked you about the limit of this function, this big piecewise function, as I approach -4. Well, you know that -4 would be values less than 2. So -4 is not going to even exist in these two parts of the function. It's only going to exist in that one. So that and -4 is well to the left of +2. So basically here, I'm just finding the limit of that. This part of the function would just be the 3x squared minus 4x. So I can just plug the -4 in there and get my value. And when I plug the -4 in there, I get what? 48 plus 16. And I get a nice little value there that's not too bad to deal with. I'm actually trying to find this on your work here. Oh well, we'll come back to it later. I got a different, anyway. Sorry about that. So I'm going to plug a -4 in there. I get 16 times 3, which is 48. -4 times 4 is positive 16. So it gives me a value of 64. And sorry if I made a math error there, but I hope I'm right. All right, what about this one? What's the limit of this entire piecewise function when I'm approaching 8? Well, 8 is way to the right of 2. So it doesn't have anything to do with these two functions. So in this case, I can just plug an 8 in, and I get 56 minus 10, which is 46. And that wasn't a big deal. Here's where it starts becoming a big deal. Here, what's the limit as I approach 2? Now 2 is right there where all these graphs meet or come together. Now remember, a limit is different than me saying what's f of 2. If I want to know what f of 2 is, I want to know what's the value of f at 2. Well, that's 5, okay? But a limit could care less about what happens at 2. If you remember the definition of a limit, it cares about what happens as I approach 2 from the left and from the right. Well, guess what from the left of 2 means? The left of 2 means less than 2. And from the right side of 2, that means greater than 2. So a limit doesn't even care about what happens at 2. That's what a value does. So if I'm trying to find the limit of this as x approaches 2, I need to figure out what this part of the graph and this part of the graph are doing. Because like this picture I drew here, one's a parabola, one's a line. I don't know where do they come together? Do they jump? I don't know. Okay, so let me figure it out. If I were to plug 2 from the left side, that would be this part. All right, so coming into the left side of 2, I plug a 2 in there and I get 12 minus 8, which is 4. So basically, to do this, I'm going to take the limit of the function as x approaches 2 from the left, and I'm going to find the limit of the function as x approaches 2 from the right. Now, as you can see, from the left part, I'm using this, and from the right part, I'm using that. So from the left, we found out that we got a value of 4. From the right part, where it's just bigger than 2 and beyond, I get 14 minus 10, which is also 4. And according to what we defined, a limit will exist if it approaches the same thing from both sides. So in this case, it did, so my limit is 4. All right, and that's basically how you deal with piecewise function limits. Now, I put a couple others in there. What happens as I go to negative infinity? Well, negative infinity would be what's happening with this part of the graph. That's less than 2. That includes forever to the left. Well, what kind of graph is that? It's a parabola. Doing what? It's positive, so it's up to the right. It's squared, so it's also up to the left. So if I approach negative infinity, I must be going up to the left. That must be infinity. And then if I'm going to positive infinity, I'm not going to look at this part of the graph at all right? Because that only works for negative infinity. This part works for positive infinity. But what does that look like? Well, that's a line with the slope of 7. So what happens, right, crosses at negative 10, but then it slopes 7. So it's definitely going up to the right. So as I move forever to the right, what's it doing? Positive infinity as well. So hopefully with this, we'll have a way to navigate these. Now I might do 12 and 13, but bottom line is on 12 and 13, I'm gonna really slow down and walk you through them. And after that, probably not as much, okay? So I'm gonna zoom in, make sure you can see this, okay. All right, so here's number 12. Number 12 gives you this big piecewise function, has 3 parts, and there's no magic in me choosing 2, I just picked 2. All right, this is gonna basically answer this question for B, but in 2 steps. It's first asking you, what's the limit of this as I approach 2 from the left? Well, 2 from the left side of 2 would be smaller than 2. So values of x like 1.9 or 1 or 0 or negative 50 are all smaller than 2. So if I want to get really close to 2 from the left, use that. So I'm going to plug 2 in there. 3 minus 2 is 1 because I got an answer. Great. That's the limit from the left. Limit from the right, I'm not going to use that. I'm certainly not going to use this because remember, limits don't care about values. They just want to know what's getting as it gets closer to that value. 2 from the right, I'm going to plug 2 in there. 2 over 2 is also 1. Well, because it's the same from both sides, does the limit exist? Yes, it does. What is it? It's equal to 1. All right, so I didn't have to answer that question. Now, if I do ask you what f of 2 is, that's what happens when x equals 2, it's equal to 2. Okay, so what do you think that means? If this graph has a y value of 1 coming in from the left of 2, visualize that. So coming in from the left of 2, I'm here at 1, or I'm approaching 1. Okay, so a value of 1, let's just say right here, coming in, right? And that's a line that has a negative 1 slope, so it's coming in like that. And to the right of 2, it also had a value of 1, but that's a 1/2, slope is 1/2, rise 1, run 2. That one's coming in kind of like, but it's to the right side, it's kind of doing that, all right? So this line, which is negative x plus 3, is coming in like this. The other one looks like that, but what happens at 2? At 2, it has a y value of 2. So this graph actually looks something like that, but you didn't need to graph it. You were able to answer all those questions without even looking at that graph. And finally, how would I find f of 6? Well, 6 is in that interval, so I'd plug a 6 in. I get 3, and that's great. So actually, the limit as x approaches 6 and the value of 6 would actually be the same in that case. All right, look at 13, and then I'm going to let you do I'm going to do a couple of the little tricky examples, show you something about those, and then I'll let you begin. Number 13, again, piecewise function. Notice this one did not have a separate equation for equal. It used the equal equation and the greater than equation and combined that into one. All right, so that's okay. You'll see that a lot. Let's take a look at this. So what's the limit of this function as I approach 1 from the left side? Well, that would be this. So I plug a 1 in and oh no, I get 1 over 0. So what does 1 over 0 mean? That's not my answer, but I'm going to write that down for 1 second. 1 over 0 means there's a VA. So I need to figure out what's happening at that VA. Now don't rush to judgment and go, wait, you said if it wasn't being squared on the bottom or it didn't have an absolute value, then it would always end up just being positive infinity. Well, I'm only checking from one side here. I'm sorry, sorry. If it did that, you would say the limit is always D and E. But because I'm checking from one side, the limit's either going to be infinity or negative infinity. All right, so I need to figure out what's happening as I approach 1 from the left. So think, what would happen if I come in from the left side of 1? That's like what, 0.99? If I plugged a 0.99 in there, what happens? 0.99 minus 1 would be a very small negative. And if I have a plus there and a negative here, that's a negative. And I already know there's a VA. So I know at a VA, it's either going up or down. So that would tell me it must be going down because plus over negative is negative. So that means from the left of 1, at this VA, it's a negative infinity. Now, you'll see that from the right side of 1, I don't have a VA. It's a different graph. So you actually have a vertical asymptote on one side of the graph, and then you have this polynomial on the other side. Well, let's plug in a 1 and see what happens. 1 minus 2 plus 5 is 4. So from the right side, I get a 4. So this graph is actually diving down on one side, and on the other side, it has a value of 4, and then it leaves there and does something. So clearly, I'm approaching two different things. So does the limit exist? No. So there isn't one. If not, why not? Well, the limit from the left and the limit from the right were not equal. So the limit of the function as x approaches 1 from the left was not equal, or the other way, whatever, the limit of the function as x approaches 1 from the right. And then if I ask you to find f of 1, well, where is it equal to 1? Right here. So plug a 1 in and you get that 4. And if I ask you for f of negative 1, well, negative 1 is definitely to the left of 1. So I would use this equation. I'd get 1 over negative 2, or negative 1/2. All right, so you should be able to do all the problems that are left on this with a couple of exceptions. So for these exceptions, I want to give you a couple little strategies. So here's the first one. And I need to talk about something that you learned, and that is, what does the square root of x squared mean? The square root of x squared, a lot of people make the mistake of thinking that the square root of x squared is x. But we have hammered in that the square root of x squared is the absolute value of x, okay? I could also say things like, well, what's the square root of x plus 1 squared? And hopefully you'll say it's the absolute value of that x plus 1, all right? But unfortunately, sometimes I'll have cases like this where I have x squared plus 3x minus 5. And because that does not factor into a nice perfect square, I can't really rewrite it very easily as in blah squared. But I do know that it would equal to some absolute value of x, blah, blah, blah. I just don't know what that other part is. Okay? So, and this is a stretch right here, but I'm just trying to get you to work with me a little bit. It'll really make some of your limits a lot more easy to deal with. Okay? Now, what do you know about absolute value? I know that absolute value of x is a v function, right? And I know that sometimes the graph looks like y equals x, but sometimes the graph looks like y equals negative x. Well, what's important to remember is it's going to look like the y equals x part as your x's go to infinity. It's going to look like the y equals negative x part as your x goes to negative infinity. Okay? And that's true on all of these. Well, we're going to be doing limits of these problems. So what you're going to do is you're going to go, all right, if I see a limit of an x squared, I'm going to know that it's an absolute value of something. But if I want to know how that absolute value behaves in each problem, I've got to look and see, am I going to the right or the left? And if I'm going to the right, I could replace absolute value of x with x. If I'm going to the left, I can replace absolute value of x with negative x. So you're going to go from here to here, knowing your definition of absolute value, and then you're going to decide, what do you do with this? Do you either negate it and make it a negative x minus 1, or do you make it leave it as an x plus 1? Well, that will all be dependent on your limit. So let's look at a couple of these problems and see how they play out. All right, so looking at number 15, A and B. All right, so I'm going to look down at 15, A and B. So here's going to be one way to go about these. Now again, in calculus, they'd probably do this a little bit differently, but I want to show you this. I think it's a little easier. So I want to go to infinity. Problem is, I'm looking at this and I'm like, well, that's not a rational function. That's something kind of weird. It's got this square root in there. So what I want you to look at is go, well, what would the square root of x squared have been? It would have been an absolute value, right? Now, it's not a perfect square because that negative 2, but what I could say is this square root of that x squared minus 2 is something like an absolute value of x, blah, 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 okay? And because I'm going to infinity, right, an absolute value of x looks like this, the infinity part would be the regular y equals x part. So for this, I'm basically not going to change the sign because I'm going to the right, and I'm going to replace the absolute value of x with just a regular x, okay? Now, what have I reduced this problem to? I have changed it to basically a rational function where the power on the top and the power on the bottom are the same. And if the power on the top and the power on the bottom are the same, I can use the coefficients 3 over 1. So this has a limit that's equal to 3. Now, look at the same problem with negative infinity, okay? So part B, same thinking. I'm going to infinity, right? I have this square root of x squared. I want to use my rules on horizontal asymptotes, but it's just not a rational function. So what is the square root of the x squared? Well, it's the absolute value of x something, okay? But if I'm going to negative infinity, that would not be the unchanged part of x blah, blah, blah. It would be the negative version of that. So I'm going to replace this with a negative x blah, blah, blah. Well, I have just converted this problem from this original square root problem to this. And now if the powers are the same, what am I allowed to do? Take the coefficients, negative 3. So I think with this strategy, you're going to have some luck. Now, if it's an odd root, like x cubed, well, or x to the 5th in there, or a cube root of x cubed, or a 5th root of x to the 5th, well, those don't have absolute value. So in that case, you can just basically simplify that and just write it as an x or negative x or whatever it happens to be. But you actually don't have to think about the absolute value, whether it's positive or whether it's negative. You don't have to think about that unless you have even roots with even powers. All right, so real quickly, let's take a jump to the next page. I may have to go even further. How about a jump to page 20? Okay, so I'm jumping to page 20. I'm going to look down at the bottom. Got 4 nice little problems, 42 and 43, A and B to look at. So first one is a lot like what we just did. I'm taking it to infinity. I wish it was a rational function, but it's not. So what does the square root of x squared give me? It means its absolute value of x something or other. Okay, so I can change that to this, and then I can use the direction of the x. Since I'm going to the right, I would use the right side of absolute value, which is just the part on the inside, unchanged, and I can change that to just a regular x. And at this point, what do I have? 3x to the first over 1x to the first, power's the same, 3 over 1 is 3. All right, over here on part B, same kind of thinking. Square root of an x squared is an absolute value of x. Okay, replace that with this. And then if I'm going to the left means I use the negative version of this. So I change that to negative x, blah, blah, blah. Don't have an absolute value anymore. Like powers, use the coefficients, negative 3. But check this out on 43. On 43, what's a cube root of x cubed? Well, it's just x something. There's no absolute value. So at this point, I don't have to decide whether to change it, or it doesn't matter about whether I'm going to infinity or negative infinity. There's no absolute value to come into play. So I can go immediately to my rules of infinity, same powers, 3 over 1. And right here, this also is x something, right? Doesn't matter whether I'm going to positive or negative infinity. Same powers, 3 over 1. All right? So see what you can do on these. I've got all of my keys updated and posted, and I think you'll be in pretty good shape. All right, good luck, guys.